Hello, good afternoon. Uh, Thank you for attending Integra's webinar on testing of complex FPGAs, memories, and microprocessors. The webinar will be hosted by Jonathan Hochstetler. He's our VP of Engineering and a test engineer for over 15 years at Integra. The webinar is only 1 hour long. There's a lot of material to cover, so we'll surely not be able to do a deep dive presentation. But feel free to call Jonathan or myself or email us, and we can surely have a customized presentation for you and your company. And before we get started, I just wanted to have a few words on what gives Integra the confidence that we know how to test an FPGA, a complex FPGA, or a memory or a microprocessor, especially when Integra is not even the designer or the manufacturer of these complex parts. Integra's technical know-how comes from, number one, we have a very solid team of test, product, and hardware engineers. Some 26 plus people strong, engineers strong. They're all in-house, and they have written almost 10,000 test programs over our 35 plus year existence. Number two, we believe that a successful development of a test program starts with a very good product engineer who understands how the device works. Our product engineers work hand in hand with the test engineers to develop a very comprehensive suite of tests that meets our customers' desired testability. Number three, we do have a dedicated hardware engineers who understand what it takes to develop the appropriate hardware to test the devices. This becomes especially critical when we are developing test programs for high-speed devices. Number four, we use the development tools as provided by the manufacturers. We use the emulators and the simulators to generate the required patterns. We also use user manuals of the device very extensively. And whenever possible, then we can get our hands on the eval boards. We do so. And that serves as a basis to compare the results as we go along developing our test program. Lastly, we understand data sheets very well. We know how to create the AC/DC parametric test for the data sheet. Our product and the test engineers use the data sheets to achieve the known outputs. And then the block diagrams that is available on the data sheet also helps us tremendously to develop the functional patterns. Now, the question that probably may be asked is, after all of this, do you get a very good test coverage? Probably not as good as the manufacturer gets it. But we know for a fact that having done so many test programs over such a long period of time, we know that we can develop a very good comprehensive test program using the tools that we have. So without further ado, I'm going to turn it over to Jonathan. And Jonathan, please.
Sure. Thank you very much for the introduction and the context. That's always helpful as a backdrop to the topics we'll be discussing this afternoon. And thank you so much for the attendance and interest. Just kind of underscores the importance of the discussions that we'll be having shortly. So just as a backdrop to all that, even when we're talking about microprocessors and FPGAs, there's some other things that often make sense to discuss in advance of that. There's certain specs that call out general categories of different types of testing, and oftentimes those are referred to as AC characteristics or DC characteristics or functional characteristics. And I think it warrants a brief discussion on exactly what that means. So that's one of the things we'll be talking about. We'll also be talking about how some of the testing characteristics are implemented in an automated testing equipment environment or an ATE environment. We'll talk about how the software is developed, some of the fundamentals of the intricacies of how the implementation takes place. And then also how we're able to implement test methods independent of what the manufacturers are able to do, because a lot of times those carefully guarded secrets, and yet there's still a need to provide test coverage. So we'll discuss those items as well. General tools of testing we'll talk about, and then items specific to certain types of memory parts as well. And last but not least, we'll discuss some of the temperature testing considerations that need to be factored in, or we can give you an example of one of the most challenging scenarios that we've worked with, and some subset of that will be applicable to most other situations. So to start with, what does AC, DC, and functional testing mean? That's just the starting discussion, and sometimes you'll see those terms referenced in specifications, and it warrants a little bit of discussion to define that a little bit. So as you see on this slide here, the DC testing only covers a very small portion of the chip. So just the first few transistors as you're touching the input of a part or biasing the input of a part. A lot of times there is no dynamic stimulus or clock associated with these characteristics. It's just a static measurement where you're measuring either a voltage or a current, and it's just a very small portion of the chip. So what can you get from this type of testing? If you're measuring the leakage characteristics, sometimes there's an indication of whether or not the part has been exposed to some type of electrical overstress or has some other functional issue. And on the slide on the right, you can see the portion of the chip that is actually covered by the DC test coverage, and it's relatively small compared to the overall size of the chip. And some common characteristics that are meaningful with DC characteristics are power supply measurements or leakage measurements, and then comparing the measurements of a particular device to measurements of a larger sample. And sometimes you can tell if there's any particular concerns or if everything appears to be homogeneous and in line with what the expectations are. So in contrast to that, or as a complement to that, it also makes sense to look at what is involved with AC testing. Sometimes this can also be referred to as dynamic testing or switching characteristics. And what you see on the screen here is just an example data sheet of the AC characteristics for a flash device. And you'll notice that most of the parameters either have units of megahertz or nanoseconds, and that pertains to a timing measurement and is indicative of a particular performance characteristic or attribute of the device we're looking at. So kind of boiling that down into just one of those particular characteristics on the previous slide, one example of an AC test is a propagation delay. And you can see on the slide on the right, basically propagation delay is how long it takes a signal to transition from across the part from one particular point to another. One type of device where this might be particularly an area of interest would be like a clock driver or a clock distribution chip, where you have a number of paths that serve similar functions, and it's very key that they're all in alignment with each other, or it takes a similar amount of time for a signal to transition from one spot from one end to the other of the chip, and they all have to be within a certain tolerance. Otherwise, it could be problematic for the application. So that's a key characteristic, and just an example. So you might look at, like for example, on the red trace path number 1, the propagation delay might be when a signal transitions from low to high on input A. When do you see that same behavior on the output B? So that's and then you measure that amount of time, and that's essentially your propagation delay. So that's just one example. So, in other words, this type of test will give you an indication of the speed at which operations can happen within a particular device. So for a memory device, an example of an AC characteristic is how long does it take to access an address? This is often specified as access time in the data sheet. Or as shown in the previous slide, how long does it take for one signal to occur after another? Oftentimes that's a propagation delay. Other characteristics that are often highlighted or featured in the summary of device characteristics are maximum operating frequency. That's how fast can you run this particular device. And that has implications for other elements that are involved in the application. Some other common characteristics are signal rise and fall times. This is the amount of time it takes a particular signal to go from a low state to a high state, and then fall time would be the opposite of that, where you're taking the maximum amplitude and the minimum amplitude and seeing how long it takes a signal to transition between those thresholds. So even when you're looking at AC testing, that's much better in terms of test coverage than just DC testing, but it still only covers a small percentage of the die or the part you're trying to test. So another key element of test coverage is functional testing, and that is basically checking to make sure that key areas of the device, like if you're listing off the features or the main functions of a part, functional testing would validate that or verify that those characteristics are operating as they should be. And one little piece of irony that goes along with that is, a lot of times you'll see in a data sheet these tables of characteristics, but there's often a relatively small amount of information in the data sheet related to how the part actually functions or how it might be used in an application. And that's where there's really no good substitute for expertise with a particular technology to understand how all those functions work together and how a test solution is best put together. So on a complex part, there's a certain amount of time that goes in up front to that effort, in project planning and developing a hardware solution. But a vast majority of the time spent developing a solution has to do with understanding the functional aspects of the part and implementing that in the test coverage. So this is an example of a complex device, and you can see the different functional blocks that are included in this particular device. For example, on this one, there's 16 different areas that you have to have, or it's a best practice to have exhaustive coverage on. And if you skip any of those, then you potentially open yourself up for test escapes and other vulnerabilities, further down the road when the part is in its intended application. So taking a step back to a little less complex device, on the left portion of the slide you see a block diagram for a simple 8-bit microcontroller, and on the right-hand side you see a physical representation or the pinout of that particular device that describes how all the pin functions associated with each lead on the part. And when you're looking at that in terms of what it takes to develop a test solution, this slide just shows a worksheet of all the different aspects that contribute to that. Because you may see a requirement for screening or testing, and then wonder, what all factors into that, or how do you end up with a cost. And this slide kind of details that. You can see there's some upfront work or offline work in terms of planning and designing hardware, and then much of the effort is dedicated towards specific parameters. And you can see certain parameters take a lot more effort to implement than others, and sometimes when you run into cost constraints, you can look at certain aspects of this and determine which options are more critical than others. So oftentimes, once that estimate is compiled and delivered and you're looking at that, the first instinct is to say, wow, that's a lot higher than what I expected. What can be done to reduce cost or without reducing any kind of risk in the application. So one of the things to consider is just testing to the application speeds. Oftentimes there's a maximum frequency specified for the part that is much higher than what the usage conditions are, and that if you attempt to test to the maximum operating frequency, that can drive the test solution to run on a higher end test platform. And if your application runs nowhere close to that speed, then you may be paying for extra coverage that you might not actually need. And again, that works for microprocessors and memory devices. Similar strategy works for FPGA devices. If you test just to the application design, that's another way to reduce cost. You may not need to test every single function of the part if you're not going to use those. In AC characteristics, as you saw on one of the previous slides, there's quite a few on that slide, and on more complex parts, there's pages and pages of AC characteristics. And if you were to attempt to test all those parameters, that would be an extremely expensive proposition, and you may only need to verify a few key AC characteristics and to cover the needs of your particular application. So that's something to consider as well. Another way to reduce costs or minimize cost is to use device emulators. If you have an emulator or some kind of design kit that can essentially simulate how the part might operate in your application, a lot of times there's elements of that can be leveraged toward a test solution as well, as opposed to just trying to develop a solution from scratch. There's also instances where if you have a known good device that's either configured or programmed the way that it is to be used in the application, we can leverage that in a test environment to generate test vectors and then screen parts to make sure that they all act similarly to what that known good device or golden device does. So moving on to testing. On the right-hand side of the slide, you see a green printed circuit board, and then there's a socket in the middle of that. And this is a common strategy for implementation of electrical tests. Essentially, the printed circuit board interfaces to the test equipment, and then the socket in the center of the board is what actually holds the part you're trying to test. It's kind of difficult to see in this slide, but there's a number of different gold pogo pins that are poking through the bottom side of the part, and those would make contact with the part you're trying to test. And then the lid would close on top of the part and apply pressure such that the part makes good connectivity with the pogo pins, which in turn interface to the printed circuit board, which then feed out through the automated test equipment. So as you can see on the slide, Integra has over 100 test programs for processors, and we've been able to develop these solutions without, in many cases, without the support of the device manufacturer. In a lot of cases, there's proprietary information that they're not able to share, and you have no choice but to use what information you can and develop a solution with best practices. So on this slide, you also see the different families of parts, just examples of the types of solutions we've developed. There's also examples of specific part numbers that we have in our library, and in some cases there's derivatives or different variations on those part numbers that we've supported as well. On this slide, you see an example of a high-end microprocessor, and I think it warrants kind of just stepping through the process of what was involved with this particular project to give you a sense of what may be applicable in your situation as well. So, the task at hand was to develop a comprehensive test solution, And in this case, Integra generated all the test vectors. There were 3 engineers assigned to the particular project, and there's 1,400 engineering hours. Basically, with this type of part, with the different functional blocks, we're able to have 3 people working in parallel, each working on their own particular area of expertise. And in this case, the entire solution was completed in less than 24 weeks versus if you would have had a single engineer working on that, or if you weren't able to operate in that kind of a collaborative environment, that would have taken significantly longer. And on the slide, you can kind of see a few of the functional blocks that were included with this particular part, such as the different communication interfaces and the dual CPU, etc., etc. So stepping back now to generating vectors, in many cases you're able to kind of model the device or use simulation software to generate those vectors. This is, software that's generally available from a manufacturer, and you're able to generate either BIST vectors, scan vectors, or other types of vectors that you can load into the part to configure it, and then you exercise the part in the automated testing equipment environment to make sure that it's operating as it's supposed to. We also work with the fabless community when they're designing a new part. A lot of times they can generate vectors in a variety of formats, and we have translation software that makes the vectors compatible with the automated testing equipment environment, and we can exercise the part that way as well. So all this means nothing if you don't have a solid understanding of how the device works, so that's a key place to start. If you have some type of a development system, again, that could be an emulator or software that is representative of how the part might behave in an application. That's something you can use to generate vectors. And again, as kind of referenced earlier as well, if there's a known good device, some of the automated testing equipment has features that you can exercise the part and generate a vector set, store those vectors in tester memory, and then screen additional parts to make sure that their functionality is in line with the known good device as well. So, and one key element here is just creating an environment that's similar to the application. So for example, device bus cycle timing, that's basically setting up all the characteristics in the test equipment, or all the attributes there, all the features, all the pin electronics channels, such that they match up with the AC specifications that are detailed in the data sheet. So there's other features that can also be leveraged in the automated testing equipment environment. If you don't have vectors, or if there's certain devices like memory devices, there's a lot of different standard types of patterns that are run, and there's algorithmic pattern generators on a lot of the memory testers, where you can basically, it's essentially a function that'll generate vectors that'll exercise the part in a certain fashion, and you don't have to manually bit bang out all the vectors. That can save a lot of space as well. In most cases, there's some limitation on how many vectors you can run. However, if you're leveraging an APG or algorithmic pattern generator, then you're not taking up as much memory space, or not nearly, you don't have that limitation that you have to work within. So the other side of it is, there is still an option where you can manually generate vectors if you have a very specific pattern that you want to implement in your test coverage. That's something that can still be manually assembled and included in the test vectors for the device. On this slide, it just kind of indicates what that might look like. For example, On that block that says vectors, you see the zeros and ones. Those would generally be what the stimulus you're providing to the part. And then you see the L's and H's, and those would be the outputs of the part. And when you're executing the test program, in order for that functional test to pass, a vector would have to be in a high state where an H is represented in the pattern in order for it to generate a passing result. If the device outputs in a low state where you see an H in the pattern, then that would generate a failure and indicate some kind of a problem with the part. So this kind of just gives you the lower level view of what's going on when we're talking about test vectors. So going back to what the recommended test methodology is, again, functional testing at speed is a critical element of that. You may not need to go at the max speed, max ratings for the part, but testing at speed is definitely a recommended practice. In a lot of cases, the manufacturer has key details that they're not willing to share, and you have to work with what is available. But if you're focusing on key AC characteristics, in general, that provides adequate test coverage. These would include things like propagation delays, setup and hold times for memory parts. And most of the time, we find that our customers are happy with implementing the various parameters as go, no-go testing. So basically, you set up the test program or the edges, the clock edges or the signal edges in accordance with the associated parameter in the data sheet, such that if the test passes, it implies that that particular parameter is meeting the specification in the data sheet. In other cases, we have customers that want to know exactly what that value is. How far away is it from the limits that are specified in the data sheet? And in those cases, we can implement the test methodology with a parametric approach where you sweep a certain edge and you find out exactly what that measurement is for a given parameter. Also, what you'll see in many of the data sheets is that not all parameters are specified at all temperatures, but over the years we've recognized that and our customers require that even if a parameter is only specified as at 25°C or room temperature, it makes sense to test that parameter at extended temperature, and you may need to adjust limits, but that data can be extremely valuable just to see how the behavior of the part changes as the temperature varies. So, and one key thing to keep in mind with this is to select the appropriate tester. To keep costs down, you don't want a tester with more features than what you need, but on the other hand, you need enough accuracy with a test system to make sure that you're evaluating the part according to what your usage conditions are, and you're not missing some aspect of that due to just using a low performance tester to keep costs down. So that process is key on the front end. And related to FPGA development experience, this slide highlights several manufacturers. There's other manufacturers that we've developed solutions for that aren't listed here as well. So this is just kind of a sampling of that. And again, it uses various software suites where you can create a design and implement that in the part and then test it accordingly. You can see several different families listed on the slide here, and then also several specific part numbers that are included here as well. And the concept of hardware is similar to what was shown on a previous slide, where you have a printed circuit board that interfaces to a socket, and that connects the part to the test equipment. So a key thing to note here as well is that we're able to develop test solutions that are independent of the manufacturer's proprietary methods. As Sultan mentioned earlier on the call, we can't claim to match what the manufacturer does. They have proprietary information, and we'll be the first to admit that we can't come close to exactly how they're implementing that. But what we can do is develop a solution that exercises all of the IOs for a particular part, and if you're able to share your usage conditions, we can test to those specific criteria and develop a comprehensive solution. And that has worked for many of our customers who are primarily in the aerospace and defense areas. One of the common tester platforms is the 93K tester, which accommodates a lot of these types of parts. And during the course of developing a test plan or a testing strategy for the part, it's one of the key things is to keep in mind that you test to the performance characteristics of the design that you implement or the design you create. You don't pick out a particular AC characteristic in the data sheet and try to screen to that, because those characteristics are dependent on how that design is implemented. So in addition to the AC characteristics, obviously you include all the DC characteristics as well. And then the functional vectors you create verify that that functionality is in place. And again, this slide underscores the importance of testing to the user application. You may not need all the coverage or all the features that are described in a data sheet. It makes sense to target that toward the usage conditions. That's a theme that was underscored in a number of times, and every time that this topic comes up in conferences with organizations such as NASA and otherwise, that's definitely a recurring theme. So on this slide, talks about memory devices and shows some yield variation in across various manufacturers through different qualification activities. You can see that not all manufacturers' products are created equal. There's some that are more reputable than others, and others that are targeted toward a niche application that may not be applicable to a broader application in industry. And then also for memory parts, a key thing to note is that if you're applying the DC coverage or functional coverage, that'll screen out a large number of defects, but it's also the ones that are the most obvious. And if you want to catch ones that are more likely to be a reliability issue further into the application life cycle, then that's when you really need to add the stresses and the more costly solutions that look at the minute details. So just in general, in terms of testing memory parts, on this slide you see various different types of memory devices and what types of potential issues we might be looking for. On the DRAM devices, it's the refresh characteristics that have a tendency to be problematic, especially as you're reaching the elevated temperatures. That's something that's well known in the industry and something that we see on a pretty regular basis as well. On the SRAM devices, the cold startup issues are something that is still seen. And again, this is an example of product knowledge that may not be the most obvious to someone that's just starting to evaluate these types of parts. For example, these aren't issues that you'd normally see highlighted in a data sheet, or they're not features or potential concerns that you'd see highlighted in a data sheet. They wouldn't, in most cases, they don't spec the amount of time it would take to start up at cold, but that's a potential issue that should be looked at or at least considered. The other thing to look at is, weak bits at extended temperature, and a lot of times these show up as functional tests when you're writing various patterns. So other reasons for testing memory devices, we've seen trends across the industry of parts shrinking in their physical geometries, and when that happens, even the smallest defects can be amplified, and they only show up in some cases at extended temperature there, which underscores the importance of performing those exercises as well. And then you see a summary of the failure modes for various technologies there. And then just in terms of the functional tests that we see most commonly exercised for particular memory technologies, on the SRAM devices, it's data retention tests. And so you're writing to the memory and making sure that stays in memory after some stress is applied. For flash devices, the pseudo-random patterns and the inverse are often what we see for EEPROMs, checkerboard, inverse checkerboard, and then for DRAM, again, March X patterns. Actually, that applies to a lot of the technologies, and is one of the most exhaustive types of tests, but is also time-consuming, and so it's not always used for that reason. But in all cases, all the types of memory tests that are performed here, the functional testing has key timing characteristics from the data sheet included in the setup conditions for a particular functional test. So that's just a common theme that's spread across, regardless of what type of pattern you're implementing. That's a theme that will be there. And in particular with NAND flash devices, it's key to look at program and array cycles, as well as to see what the endurance might be over the life cycle of the part. How a lot of times there's a specification for how many read and write cycles you can have for the part before you see some kind of deterioration there. And for qualification testing especially, that's something that we'd look at, and you design those criteria around what the usage application is. You don't want to be more stringent than you have to, and then have to discuss failures that you're never going to see in the usage conditions. And on the other hand, you don't want to test too few cycles and then not be aware of some kind of reliability issue that may show up years down the road. So this slide indicates or kind of gives you an idea of one of the configurations of one of our testers. Some of the details in this slide are just the number of IOs that can be programmed to exercise a part, and again, this would apply to not only memory parts but also FPGAs as well. You can see this particular tester has 384 channels that can be programmed, and then several different power supplies that cover a variety of ranges. This particular tester has covered DDR3, DDR4 parts, and there's hardware and software upgrades to this system that can also support other niche requirements or expanded capability where that's needed. So as mentioned earlier, a key aspect of most of the test coverage requirements that we see includes some type of temperature testing as well, and usually 3 temperature testing, 25°C, minus 55°C, and 125°C are pretty common. And one thing to be aware of is just making sure that the die within the part is actually at the temperature that you're targeting. So this is an example of kind of an extreme case where we're testing 16 parts in parallel. Sometimes that parallelism is a way to achieve some cost effectiveness with memory devices, especially when the test time is really long. So for this particular setup, there were 16 parts were tested in parallel. Half of those were ones that we characterized for temperature to make sure that there was consistency across those sites. And you'll see in these plots on the screen that how well those different sites track together. I should note that this wasn't the way it worked out on the first attempt. There was a lot of variation between sites, and it took a lot of effort and optimization to achieve this level of correlation between those sites. And more plots just kind of illustrating that over different temperature ranges. So in summary, on with temperature testing, with effort and time, we could keep sites within that 6-degree window. Other details in this slide include, the amount of time it took to achieve that temperature, and the soak time to reach some level of equilibrium. So, and this slide includes, details on thermocouple placement and other, the amount of time it actually took to reach the target temperature and for everything to stabilize. And again, I should note that this is just an extreme case. In a lot of cases, it looks like, the setup looks like one of the previous slides where you saw the socket on a printed circuit board and we're just testing one device at a time, and you essentially use a subset of these requirements, and it's much easier to keep one part within a particular temperature window as opposed to 8 parts in parallel, but it just shows the capability is there when needed. So with that, covers the bulk of the information that I had planned for today. And again, this was just a high-level overview of some of the experiences that we've seen in recent years. And obviously, there's a lot more detail that can be provided on any one given topic there. We could set up separate webinars or provide additional information on what our experience has been with a variety of different technologies if there's interest along those lines. And you can definitely reach out to Sultan or I with specific questions or for a copy of the presentation. That'll be available as well.
Thanks, Jonathan. So if I was to summarize what Jonathan presented, really is as far as Integra is concerned, we have so many different platforms, and we have dedicated platforms. So for example, we have memory automated testers that do nothing but memory. And within memories, we have NAND flash testers, for example. We have passive testers and discrete testers and the likes of it. But the key point, what Jonathan was talking about is, we keep hearing this. Oh my God, it costs so much to to test a device. But let's just take an example of a Vortex 7. We have people who come in and said, hey, I'm not even using the DDR interface. I'm not using the SerDes portion of it. So I really don't need you to, or the GRTH portion of the functional block. If that is the case, the cost just went down by at least 50%, maybe 60%. The hardware cost goes down because we don't need a sophisticated off a socket, because now we're talking about limited functionality tests that we can develop using a lower cost socket, versus if we had SerDes to test, then we would obviously be concerned about a lot of the data transfers and the failure modes associated with that kind of testing. So the other point that Jonathan was making was if we can use application-based patterns or emulators, oh my gosh, that'll drive the cost down dramatically, because all of a sudden we don't need to develop as many patterns. We just need to develop some very basic fundamental patterns, but not necessarily the exercises the entire device because of the specific patterns that are being given to us. So the other place that we get issues with costing is somebody will buy a commercial grade part. It's a 0 to 70 degrees C, and they want to test it for an upscreening. So if you're going to upscreen to minus 55 to 125 or minus 40 to 80 degrees C, now we have to deal with the issues of the data sheet is only given us a 25 degrees C parameter, but we are going to develop a test program that goes to minus 40 to 85 degrees C. So we have to develop the characterization curves to be able to say, this ICC at 25 degrees C we know behaves at this temperature, but we don't know what's going to behave at minus 40 or 85 degrees C. So we have to develop some curves to be able to test it at a higher temperature and be sure that we are falling within the windows of the parameters as the device would behave at extended temperature. So a lot of these nuances that we have. So Jonathan, during your presentation, I've been getting questions that I've been answering. One of the questions that I have not been able to answer was, could you discuss the limitations of contact padding with different pitches? If you have different pitches, and if you are to get a socket, how would you deal with different contacting pads of different pitches? What has our experience been for that?
So in most cases, what we find for these types of complex devices, we end up working with a number of manufacturers that we've got a long relationship with, and they design a custom socket solution. Oftentimes that includes gold pogo pins with low inductance or parasitic characteristics, and those are some key features there. And then you also have to consider whether it's a lead or lead-free part. Those are key factors, and then just sensitivities that the device might have to pressure or how it's placed in the socket. Those are all factors that are included there. So I guess the short answer is that a custom solution is generally designed for each one. We're not using an off-the-shelf burn-in type socket for electrical test. Our experience has been that doesn't always produce good outcomes. So that's the general strategy there is everything's custom. Another question I saw that flew by is, what's a typical schedule for one of these development efforts? And obviously it can vary significantly. You saw the extreme case of that complex microprocessor, and that was 24 weeks there. And I should add that on the front end of that is the lead time just for the hardware and the custom socket. At a minimum, some of those solutions for complex devices, you're talking about 8 weeks just for the hardware aspect of it, and it can be longer than that. And you have to have the hardware before you can actually start working with the part. So that kind of gives you a sense of what that timeline might look like. So the sooner we can engage with an opportunity or a customer, the better. In a lot of cases, we can get things like the socket on order while we're working out some of the finer details of the test coverage and all that. So that's, as it's probably no surprise, but starting sooner rather than later is always an advantage. Even if you're just discussing things on a conceptual level, if we start that dialogue early, we're more than likely to have better success meeting the schedule requirements.
What about, Jonathan, could you talk about the BGA sockets, and how do we prevent damage to the BGA, the balls, during testing? What kind of a socketing are we using, or methodology we're using?
That's a good question, because inherently BGA devices, are designed to be installed in an application, and they're not designed to be cycled through a test socket numerous times. So one of the best practices that we implement is that we have our custom socket manufacturers, work with devices that are either from the lot that we're going to be processing or at least representative of that. and we provide those to the manufacturer, or have them at least do the checkout with that. They can design to a drawing perhaps, but their final checkout has to be with those devices. And then during test program development, we do a lot of repeatability testing, taking the parts in and out of the socket to make sure that we don't introduce some kind of mechanical issues further down the road during processing, because those devices are can have some potential vulnerabilities when you're repeatedly using them in a testing environment that they weren't designed mechanically to hold up within that.
What about the various patterns that are being used for memory testing? Could you elaborate on that?
Right. So there's, as covered on some of the previous slides, there's specific patterns that are designed to bring out some of the potential design vulnerabilities there. In general, the extreme would be kind of like a March X pattern that's implemented, and that's applicable to many types of parts. If that becomes too costly in terms of test time, the checkerboard and inverse checkerboard and those types of patterns are still go-to. Sometimes our customers will call out a specific pattern that they want to use within their specification, and if they don't have anything in particular in mind, then there's a lot of best practices out there in the industry that provide good guidance on what type of solution to implement.
Well, I think that's all the questions we had, and then obviously we answered some of the questions. So to the audience, please, you have Jonathan's email address, you have my email address, you have Jonathan's phone number in the presentation now. Some of you have sent me emails to say, hey, could you send me a copy of the presentation? I would be happy to do that. And so please feel free to contact us for any further questions that you may have. And I really, it's a great participation. Almost 90 people have attended the meeting from a wide variety of companies. So really appreciate your attendance. And thank you very much again from our entire Integra team and on my and Jonathan's behalf. So appreciate you attending. Bye-bye.